We're in Rosen Discrete Mathematics and its Applications, section 8.3, and here we're going to run through a proof of Theorem One that allows us to calculate the big O of a divide and conquer relation with some specific limitations. Before we do that, we're going to run through an iterative approach of the divide and conquer algorithm so that we can get it down to a form we can analyze. Here is the divide and conquer algorithm right here. Fn is equal to A f at n over b plus g of n. And we're going to make the simplifying assumption that n is equal to b to the k, a power as an integer power of b. Now this turns out not to be a problem for big O analysis, and it makes things much simpler for calculating big O. So the way we're going to do this is Fn is stated in terms of a smaller input for F. We're going to do the same thing for Fn over B, and we're going to say that Fn over B is equal to A times F at n over B squared plus G at n over B, and we'll distribute this A through that parenthetical statement, and we end up getting this statement right here, A squared times F at B divided by F at n divided by B squared plus A times G at n divided by B plus G at n. Well, now we're going to apply the recursive relationship to F at n over B squared, and we get A times F at n over b cubed, that's supposed to be a cubed, plus g at n over b squared, all times a squared. We'll distribute that a squared through that parenthetical, and we get a cubed f at n over b cubed plus a squared g at n over b squared, a times g at n over b, and g at n. And you will notice that if we continue to do this, the exponent for a and b will continue to climb until it gets to k, and the exponent for the leading term in front of the g's is for a and b is going to be one less than it is for the leading term. And you can see that it's also becoming a series, where the last one has, this one has a1, b to the 1, and this one has an implied a to the 0 in it and b to the 0 in it. That allows us to rewrite that as a sum of j goes from 0 to k minus 1 of a to the j times g at n over b to the j. Now this leading term we can tackle with our assumption that n is equal to b to the k, because n divided by b to the k is 1, so the argument for my function becomes 1, which is an initial condition. So now I've expressed Fn as a sequence of functions, of applications of g at n, different sizes, plus some a to the k times the initial condition. Okay, so we'll use this a couple of times. Let's take a look at our first theorem. For our first theorem, we're going to try to calculate the big O of a function describing an algorithm that has A subproblems, and the reduction of the problems is 1 over b. And notably, our conquer functions is simply a constant c. All right, and then for this we have if a is equal to 1, like it was for the binary search algorithm, then the big O is log of n. And if a is greater than 1, we got more than one subproblem, then f of n is big O of n log base b of a. And when a is greater than 1 and n is equal to b to the k, we have a specific expression for fn that is going to be a polynomial at n to the log base b of a, where I have some constants that I can calculate, and they're given right here. And I'll prove these. So let's start. Again, we're going to simplify, let n equal power of b. And remember that g of n is just a constant. And if n is a power of b, just note that k is equal to log base b of n. All right, so we're going to take using this function that I had starred before and substituting c for g for all the functions of g, I get that a to the k times the initial condition plus the sum at a times g at n, or all the various inputs for g, but it's just a constant, so it's a to the j times c. And I can factor out the c since it doesn't depend on j. I have an error here, that's a to the j. And so my number of operations is a to the k times f at 1 plus c times the sum of the a to the j's. Now, I've got two cases, one where a is equal to 1. In that case, all of these a's go to 1, and I'm just adding up c k times, which gives me k times c. And then I have my 1 in front of the f1. So for a equal 1, I get f at 1 plus c times k, which I can substitute log base b at n. And so f of n is going to be big O at log base b of n. Now, if a is greater than 1, then my sum is a truncated geometric series, and I have a formula for that. So a to the j, the sum of the a to the j's from 0 to k minus 1 is just given by a to the k minus 1 over a minus 1. I substitute that back in to get my number of operations that's problem size n is a to the k times my initial condition plus c times that expression for the truncated sum. And I have an a to the k in there and a to the k here. I'll combine all the terms for a to the k to get this multiple of a to the k, and then I've got this is the constant term. And these look like C1 and C2 from earlier. Now, since k is equal to log base b of n, I get a to the k is equal to a to the log base b of n. That turns out to equal n to the log base b of a. To see that's true, I'll have you do this. You can take the log base b of both sides of that and show that they're equal. But making that substitution gives me f of n is c1 n to the log base b of a plus c2, which gives us fn has a big O of n to the log base b of a, and the proof is complete.